So today, we are looking at answering this key questions. We have heard a lot about time series and different type of data formats and databases as well. Why does time series really matter for metrics, real time, and sensor data? That's the topic for today. And as we go into this presentation, uh, there are a few things we'd like to discuss. First of all, what exactly is time series data and what it isn't, right? It's always misinterpreted. What kind of questions can we ask of the data? Can we predict the future or do some kind of predictive analytics using this time series model? What kind of workloads, do we see on time series databases versus traditional ones like, OLTP or full text search database engines? Finally, we'll touch upon some reference architectures that we have been talking with hundreds of people in the community architectures and their projects with us. So how are they actually using influx data for their custom DevOps, real-time analytics, or IoT projects? And at the bottom half of the presentation, data versus other platforms with respect to time series, right? We are not looking to go into full text search or document databases per se, but as functionality as relevant to time series only. So to start with, here are a couple of examples of time series data. On the left, what you see are metrics, system metrics, traditionally like CPU, disk, memory, and on the right side, you have a totally different set of financial data, which is essentially quarter on quarter, Dow Jones Industrial Index results. What's common across both of them are on one of the scales, they're both plotted against time. On the left one, you have times that go up to seconds or maybe even minutes and hours. And on the right one, you have a much larger aggregated scale, but these are traditional time series data. What is not time series data? And just wanted to clarify these basics before we move into the deeper topics. If you're looking at what is your social impact in terms of how many connections you have, people who like your Facebook posts, or if you're looking at graphing functionality in general, time series databases are not graph databases, which could show nodes and relationships between nodes. There are different tailor-made databases for that purpose. On the right side here, you are seeing scores, which are essentially segmentation data, saying, hey, you know what, we get athletic scores, and based on the type of profile we have of the students, their athletic scores could be different, right? But this has nothing really to do with time series. It could have something to do with time series if you started to plot this over a moving scale of time. But this is essentially a snapshot of segmented data. Just to reaffirm, right, before we go the deep side of this, on the left, you see time series data, which is, hey, number of tweets, right? Royal baby arrived, hashtag usage. And you can see this hour on hour and the number of tweets and retweets growing. The same example on the right side is the tweets by population. And these are across different countries. So you can see that the same data can be represented on the left side as time series and on the right side as segmentation data, have nothing to do with time series. Right? Cool. So what kind of questions can we ask of this data, and what kind of patterns do we really see, right? Now that we understand the very basics of what time series is. So questions that you can ask of the data that is available in the present tense as well as the past, right? There are some sample data here, sets here. How can I resolve application outages, right? And this is before the customers start to complain, and I'm seeing some issues in there. If I were somebody in the marketing team, I would like to really know how long visitors stay on my website, what is my retention rate, and why do they drop off my e-commerce website, right? If I was someone in the security team, I would be really interested to know when somebody tries to do a DDoS attack in my network, and I want to watch it as it's happening, right? If I were in the fintech market, I would like to buy and sell my stock and maybe try to time it with the market and price fluctuations. And there are some other use cases as well. Now you can see here some of these users have to do with social media sentiment. Maybe you launched a product, you want to track what the social media sentiment is. If you are an e-commerce site, you might want to look at comparison deals, right? There are so many deal engines out there. Are my competitors selling deals at a cheaper price? Can I actually do discounting? What's the common theme among all of them, right? Is the data needs to be fresh and it needs to be live. I need to get as real time or as near real time as possible. Because if my data becomes stale, even by a few minutes or maybe a few hours, I cannot take actions which have the same impact as it would have on real-time data. So for example, if you look at the last line here, could I power self-driving cars? If you've been watching the news recently, people have been testing self-driving cars and some crashes happened. But that being said, the decision need to be made in split seconds, right? Not that it had anything, that crash had anything to do with time series, but the whole idea is you cannot, your sensors are transmitting real time. You need to take decisions in real time. You cannot have a delay or a latency of 1 minute, 5 minutes, whatever that is, right? And that's when the data is most valuable to the business. Now, when you start looking at this data, right, you can obviously ask this question. Obviously, in the questions that I showed you in the earlier slide, these were all past or present questions. When you start looking at the patterns behind the data, you can maybe identify some of them, right? So here's a graph which shows sales numbers, right? Quarter on quarter over a 4-year period. And what you see here, is just a trend. It's called a horizontal trend, right? All that you can see is there is some randomly fluctuating Y value on the horizontal axis of T on time. But it's totally ad hoc, right? That's all I can say. However, if my data was plotted like this, and I see a steady relationship that, hey, you know what? Overall, maybe my sales numbers go up and down, but I have some sort of a trend, right? The fluctuations are still present, but there is a trend. In this case, this trend is called a secular positive trend. There are secular negative ones as well. In this case, now you see a pattern called as a time trend. Moving a little more further, there are trends which are periodic, right? So obviously you see the same patterns happen in shorter periods. There are some short-term periodic relationships. And not all data points are the same, but you will have some semblance of repeatability, right? And you could be seeing these patterns over a quarter or a month. These kinds of patterns are called seasonal patterns. And now, if you're looking at longer term periodic relationships, right? So you can have gas prices, or maybe in this example on this graph, I have a World Cup, soccer World Cup happening every 4 years, and you are tracking merchandise sales. And you can see that, the year when the World Cup actually happens, your merchandise sales are the highest, followed by a sharp decline in the second year, followed by, linear decline in the following 2 years. Again, the fourth year, as well, as soon as the World Cup launches again, you get a sharp curve up. And however, you're also seeing a trend here where there is a growth trend year on year. So there is a repetition, but it's a longer term cycle, as well as there is a growth trend, right? So this is a typical pattern called as the cyclic pattern, right? And there could be patterns which are just irregular, right? Which have nothing to do with, you can try and plot as much as possible, but these are unobservable time-dependent influences, like, hey, errors, right? Or freak events or downtime. If you start having a lot of patterns around those downtimes, your infrastructure isn't working well. But you are not supposed to have a lot of these happen, and these are supposed to be irregularities. Right? Now, we looked at this current and past data. Now, can we actually try and take this data and do some kind of predictive modeling around this? The answer here is actually yes. However, this predictive modeling of the data is best done with time series, right? Most of the algorithms on predictive analytics are written on time series. So if you have to forecast anything, you better be dealing with time series. Doing this on a document database or a relational database is going to be I won't say it's impossible. You can try and make it work as a time series, but all forecasting model are based on time. So some questions, right? I'm interested to know what is my revenue projection over the next 4 quarters, or will my infrastructure scale like Friday, right? Or maybe can I, if IoT company, can I start changing my flow rates? Obviously, you are measuring all of your flow rates using sensors, and these sensors are sending you metrics that you are consuming over time. And then you want to apply some algorithms to those times to come up with some predictive models, right? So there are quite a few questions that you can start asking in the future. I'll not go through each and every one, but having talked with a lot of people in the community as well as customers, I see particularly a use case for industrial IoT. People are trying to optimize the manufacturing process. They will do test runs after test runs, change, tweak the ingredients over each test run. And maybe you don't actually, based on the results of a couple of tweaks to the same parameter, you can actually not have to do many more tests. You can start doing some predictive modeling around that. Right. So what kind of forecasting models do people really use, right? What kind of them are available from a mathematical perspective? The simplest is called as an autoregressive model, where you can predict the variable, right, as a linear regression of the immediate past value. Super simple, but not very useful. Once the next step forward is smoothing of the data, right? So that you start getting into moving averages, centered moving averages. We recently wrote a blog on Holt winters, which is exponential smoothing. And you can read this up on Wikipedia, right? There are a lot of algorithms. But from a category perspective, there is autoregressive and then there is smoothing, right? And with these two techniques, now for advanced predictive analytics, there are some integrated models. So if you look at ARMA, that's essentially autoregressive moving average. Then you have autoregressive integrated moving average. And then you try to integrate it with the seasonal pattern, or you try to do a fractionally integrated pattern. So you can get into more and more complex models. So the net is, can I see a predictive model here? Here you go. This is a simple forecasting example that you can plot on your data using the ARMA model, right? So the blue data points actually represent averages. The green ones are essentially the blue ones are your raw data. The green ones are your averages, or rather this is a moving average. And the red one is the computed forecasted data, right? Based on the ARMA algorithm that you are implementing on this data. Now, why are we speaking about this? Because in Influx, and I'll talk about other stacks as well, you can write your own smoothing algorithm. We wrote a capacitor example for Holt winters, which is not an ARMA, it's simply a smoothing one, but you can actually implement an ARMA algorithm to do some kind of predictive analytics on this data. So before we go deep into that, just to understand, in time series, the workloads and the data models are actually totally different from OLTP systems, JSON document databases systems, or relational models. So what do we need to know, right, getting into time series? Three key points. There are other subtle differences, but if you're looking at data lifecycle management, looking at metrics, let's keep it simple. If you are in IT, you know what metrics are. You try to retain data for periods of time. When you get into longer periods, then you try to aggregate, downsample, maybe aggregate 4 data points. If you're storing at, let's say, 15-second frequency, you are okay to average them out into a 1 minute frequency. So essentially, you are downsampling, right? And you're getting into a 1 minute resolution. Maybe after a month, you can downsample it to a 15-minute resolution, right? Now, to do this, right, most databases have to do the computation, but also have to evict large sets of data and constantly summarize that data at scale. Unless your database is specifically designed for this function, it's fairly hard to do. And if you're using a system like Cassandra and you try to do this in code, there's a lot of code you need to write and things don't work in an optimal fashion. Summarization, right? Now, when you're computing this data, you probably want to also start having some streaming analytics, right? So this summarization, maybe you want to compute percentiles as you go along, right? 95th percentile, 90th percentile, give me all these summarization buckets. So you want to consume time series data and create summarization and try to get that summarization as a readily available streaming metric so that you don't actually have to write code to query it. Long range scans, right? Maybe you want to work with retention policies which are specific to specific metrics. And how do you work with shards and what do you write to disk versus what you don't write to disk? These are traditional workload characteristics of time series databases, right? Most time series databases don't try to write everything to disk. They try to write most of the measurements, as in case of InfluxDB, most of the measurements and tags to memory and only the values to the disk. So your query speeds are much more faster and so on, right? So for InfluxDB in particular, why are we so special, right? It's optimized for both regular as well as non-regular time series metrics. So this is different from, if you're looking at most time series metrics, they don't deal with non-regular event-based data so gracefully, right? But when we start looking at Influx, we optimize for both. The precision level, right? We go up to nanosecond level precision. As well as you can keep raw data for a long time, and we have all these downsampling and aggregation built in, which is very important if you're really getting into scientific and sensor scenarios where raw data precision is a must, right? And there are a lot of data sets built into the structure of the data, right? So there are pre-built functions, right? Min, max, average, standard deviation, spread. There are in-memory analytics. We call that continuous queries. Those are provided out of box. In any non-time series databases, you'll have to manually do this or write your own functions and come up with your own functionality. And in sheer number of scalability, we did some benchmarks, and which Jimmy was mentioning. They're available as technical papers on our website as well. That being said, we on a single server, we have done tests which can handle 1 million writes a second on a single node, right? So that's way beyond most of our good competitor technologies out there. So a little bit about how InfluxDB maintains its data model, right? So it's a schemaless database. However, we define a series as a set of measurement name, tag set, field set, and the timestamp. So for example, let's say your measurement is temperature and you are providing it tags, device equal dev1, building equals b1. And then you can essentially put some fields, right, which said, oh, this is an internal temperature, or it's an external temperature. And then you have values, right? 80 and 18 are values here. And then there is a timestamp, which can go up to nanosecond ranges. Now, point is, if you don't specify a timestamp, Influx will timestamp it for you. And there are a lot of best practices how to deal with the Influx data model. However, if you start looking at these combinations, right, and if you're coming from the graphite world, you have a historical method of, concatenating every field and measurement by dots, right, or periods, which we don't do here, right? We essentially follow this model, and this model is optimized for a protocol, right? There's a data protocol behind this. It's called the line protocol. And as long as you follow the line protocol and the best practices, InfluxDB will give you those hyperscale numbers, right? So there are other webinars we have recorded. I'll not go too deep into this, but this is essentially how the InfluxDB data model works, right? So let's look at some reference architecture. So talking with hundreds of users of Influx data, we came upon three separate reference architectures. So let's talk about IoT, right? And even in IoT, you can see there are about 9 specific use cases that we narrowed down about, right? Some of them were wearables, right? Utilities like flow control through city pipes, or if you're looking at agro, right? People are doing smart farming right now. The other category were smart offices, smart homes, right? These are mostly around commercial IoT, vehicles, logistics, and then you had the industrial automation guys, right? Oil and rig, manufacturing, nuclear power, and so on. So we start to see a couple of patterns there. On the first one, where it's mostly consumer IoT, or maybe it's not behind a data center IoT, right? What happens is most of these are running low-powered sensors. Some of them might be running Raspberry Pi, some of them may be running Beagle Bones, other chips. And these have sensors like LM35 sensors, humidity, temperature tracking sensors, what you have. And they talk to a mobile connection, right? So let's say you have a router in your house or in the farm, right? Or maybe you have your cell phone that you're carrying around for a variable connection. It makes that connection to that Bluetooth or Wi-Fi, and then goes and sends its metric. And in this case, most of these metrics are events. Some of them could be time series events. Write them up to some kind of message queue upstream. You can call it an IoT gateway, but there are different ways of buffering the data up into a cloud, right? And on the cloud, they are using InfluxDB to store this data, visualize it using Grafana, write scripts using capacitor, do alerts, and obviously you also want to have a control loop there through an IoT gateway. So if you're looking at AWS and you're deploying Influx on AWS, and you have an IoT gateway from AWS, you can essentially have capacitor call a backend script to control your device, which is a loopback API, right? So it's not just monitoring, but it's also control of the sensor. For most of the commercial and industrial ones, the protocols were vastly different. These were not, event or HTTP or whatever, MQTT. So we started seeing the evolution of protocol bridges. In some cases, these are supplied by vendors, like Dell came up with a Dell Power 5000 gateway and so on. There are quite a few other smaller startups who are coming with protocol gateways, where you're seeing protocol translation from Modbus, BACnet, what it is, into pure HTTP or event-based streaming or UDP channels. And in case of industrial, what we found that cloud connection may not be available a lot of times, right? The network bandwidth usage is very restricted. You might be at an oil or rig utility where you don't have much network access. So you need to do a lot of processing at the edge, right? And so we have seen scenarios where people have started to deploy Dockerized images of capacitor and InfluxDB on the top floor network, where all the sensor data can you can pull information from industrial historians called PLCs, or maybe you have a way of sending this sensor data directly into capacitor, which can consume both streaming and batch data. And then you can do localized processing on the fly. So A/B testing, a condition is out of whack, send an alert, and then store the raw data. And maybe once during the day, or maybe once every 4 hours, when you get a dedicated network connection, you can aggregate and downsample and send that data back into your corporate VLAN or you're onto the cloud for longer term analytics, right? So this is kind of a common reference architecture that we are seeing. For real-time analytics, there are different spaces, and most interestingly, we are seeing a lot of deal comparisons, price comparisons. We are also seeing modeling of sales modeling, like e-commerce sales modeling. Right? We have a testimonial from a very large vendor on our website. I think it's eBay. Some of their teams are using this for sales modeling. Presence services. When you are on your website, you want to get more agile. A customer is on your website, you want people to pop up and say, hey, can I help you, right? So how do you track that? Unless you're tracking in real time, can't make that happen. Security is another one. You're looking for phishing, malware, or content monitoring. A lot of that, or even fleet management, right? So all of these are essentially real time. But on the bottom left, we had a testimonial from NIST, who are essentially using Influx for quantum analytics, right? The whole architecture here is you could be consuming messages. Maybe you are scraping your websites using JavaScript, or you're instrumenting either way. Or maybe you just are providing an API. So Influx ships with an API, right? We have APIs in about 7-8 languages. So if you're writing your application, you can annotate the code and send these metrics using an API into the Influx stack. Or maybe you are already consuming this data in your big data system, through Kafka pipes or whatever. And then you can run some ETL jobs to get that data into Influx and run all kind of time series analytics on them, right? A lot of these are, the rest of the stack is pretty much there, but you can plug and play any of those components in the tick stack that Influx ships to do some pre-processing or post-processing, as well as real-time alerting and control. And the most common use case that we see is custom DevOps, right? So monitoring. Now, monitoring has so many vendors, right? So many silos, and I'll get into the details of that. But traditionally, what we are seeing is a lot of developers are custom instrumenting their applications because out-of-box tools don't provide the visibility. Maybe this is not just performance data. Maybe this is application level data, right? So because you have an API, you can instrument your code and send the data, into Influx over HTTP, and following the line protocol. If you're looking at OpenStack, we are seeing a lot of usage in OpenStack instrumentation and monitoring. And the third is creating a single pane of glass. So if you have a silo tool for pretty much everything, applications, databases, network, mobile, you name it, right? Switches, storage, there's too much proprietary stuff going on. So developers are trying to build a single pane of glass for their operations, pulling data from all these tiers and correlating them in time, right? So we'll look at, I'll show you some reference architectures in detail. But let's look at some real world examples. So here's one, you can look this up. This was published by AT&T, one of their groups who are working on a lot of container management solutions. And this one is called Charmander. It's a publicly available project on GitHub, right? Where they use a combination of Apache Mesos to, do task deployment and spin up Docker containers, which ships with a cAdvisor library. And cAdvisor has all the instrumentation for collecting metrics from Docker containers. And cAdvisor has a direct integration into InfluxDB. And also the cluster information of Docker containers is stored in a project called Heapster, which also uses InfluxDB as the backend. So Google essentially uses InfluxDB as the backend for Heapster. And then from a compute perspective, they applied Spark to pull data from InfluxDB and run analytics jobs, which again, feed into that orchestration process. Right? So classic container management, multi open source technology platform. This one is for OpenStack. Again, you can see that folks are collecting data from compute nodes, storage nodes, controller nodes, But essentially, you have layers in OpenStack called as Nova and all, and you can collect those data. But in this case, what they did was they segmented the type of data coming in. So event-based metrics, they sent it to InfluxDB and visualized it with Grafana. All the log events, they sent it to Elasticsearch and visualized it with Kibana. But now that they're essentially moving to a full-fledged Influx platform, because we do support events on the same way that we support metrics, right? Third one is a really interesting one. This is from a nuclear power plant, where data access and sensor is fairly limited in the way they work on protocols. Most sensors are analog devices, so they cannot really send data over the wire, over an HTTP connection. So they talk to a processor switch, which happens to be a PLC device. Where most industrial historians, historians like Wonderware from Schneider Electric, even Microsoft SQL Server acts as an historian of some kind, the OCSoft Pi. All of these guys essentially are polling these PLC devices. And what these developers in this nuclear power company did was send that historian data, and even essentially bypass that historian altogether, and use the HTTP API to send data into Influx, and then query that for their operational dashboards, and then use some analytic scripts in Capacitor to build dashboards for business, right? So anyway, I'll leave you with a few others, right? There are a few real world examples. This one is more for a smart shower head, and they were a startup, right? They were building this even before the chip came onto the market. So this was particularly for an ARM-based board called the Samsung Arctic chip, and they're monitoring flow rates, right, or temperature from the shower head itself, and sending the data over MQTT into an Kafka pipe, and further downstream into Influx using the Telegraph ingestion plugin for Kafka, right? And the final one that I wanted to touch upon is wearables, right? Similar architecture, but here we are seeing a lot of companies who are embedding sensors within the fabrics, connecting through a mobile interface, sending those metrics, and then as you wear those fabrics, exercise, go about your daily routine, they are tracking fitness, activity, and a lot of other stuff, right? And correlating that data. So it's not just coming from Fitbit, you're getting your heart rates and whatnot, right? Your blood pressure, and maybe, if you're diabetic, maybe some information about that, blood sugar levels, right? So a lot of people are using Influx as the platform to build their solutions on. So let's do a deeper comparison, right? Getting into the technology aspect of it a little more, of Influx versus others, right? So if you're not familiar with Influx, right, we have a stack. It's called the tick stack. And we collect, we store, we analyze, and we visualize, and also act in real time on the same data pipeline. So the entire data pipeline is time series only. Now, time series could be data coming from metrics or agents that are deployed, and or maybe applications that you're instrumenting, or maybe logs that you're parsing, right? So once you get that data into the common data pipeline, there are not too many moving parts like a Hadoop architecture, right? Everything is seamlessly integrated. Everyone works on the same data model. It takes literally 4 lines to install the entire stack, and gets you rolling in within minutes. You can actually stand up a end-to-end solution. Now, this is what it architecturally looks like. It's kind of a layman representation. There's more to it. On Telegraph, right, we have what we call a set of plugins, right? When this was done, we had 60 plus plugins. Today, that number has, if you're including both input and output plugins, we have already into the higher 90s, or maybe more than 100. Every month or so, we see 2 or 3 new plugins getting contributed from the community. So you can get data from sensors, hardware, IPMI sensors, containers, system statistics, databases, network devices. You can do SNMP based data, UDP based data, query, get data from message queues, apps, so on, right? Once you get this data, all of this data is written by Telegraph into one or more InfluxDB instances running in a cluster. And it's written using the line protocol for optimal storage. For visualization perspective, or data exploration rather, I will not just say visualization, because for this is not a dashboarding tool per se. People use Grafana. Most of our consumers use Grafana with Influx. But Chronograph has a very nice data explorer, query tester. So you can look at what kind of data you are storing, navigate the entire database schema, do a lot of role-based access control, like who gets to read, write, access what kind of data, right? So Chronograph is essentially the UI for Influx, right? And Capacitor is essentially your rules engine. You can write rules, and there are a lot of pre-built functions, map reduce jobs, lambda functions, whatnot, sigma functions. So you can watch the data, you can query Influx in batch mode, or you can just subscribe to the stream of data that's coming in real time. And obviously then you can do data transformation, ETL. You can do anomaly detection. You can not even have to set hard, fast thresholds. You can do alerting, very cool about that. And then you can do a bunch of actions. If certain events happen, you can define your own logic, right? So you can write any logic in Python, Java, whatever, and apply that onto the data pipeline. And if you get an interesting event out of that, you can take an action, maybe trigger a DevOps job, maybe send a notification, or maybe make an API call from the backend or whatnot. And then we have our Influx Data Enterprise product, which we just launched a beta for, which does replication. You could go multi-data center. We do a lot of cluster management and all that using Influx Data Enterprise. Right? So, if you're talking about Influx and Elastic, there are some benchmark reports. There's detailed analysis, reproducible data sets, and functional differences per se. So Elastic, if you look at that, right, I've seen people use it for time series, but it's really optimized for full text search, right? And not that, because I work for Influx, but even talking with end users, and even our benchmarking was done by an independent consultant. We saw some drastic numbers when it comes to time series, right? So if you're simply looking at write throughput for the same server, everything else being equal, we got anywhere from 5x to 10x faster write throughput on Influx. From query-wise, we were anywhere from 5 to 100x better with Influx versus Elastic. But that being said, why this large range, right? Because it depends on your combination or your tag values and your measurement values and how complex your queries are, right? When it came to disk compression, for just pure raw data, at high precision raw data, we were 10 to 15x better, right? Influx was 10 to 15x better than Elastic. And when it came to summarization data, Influx was 3 to 4x better than Elastic. But again, this is all considering a time series data structure. Now, if you switch to full text search, the numbers might be totally reversed. But that being said, Influx does not do full text search. We are specialized for time series only. There's another benchmark report that Jimmy was pointing to, which is essentially your Cassandra. And there are some numbers here. The query speeds were probably, and the disk space were probably the biggest things to watch out for. We were at least 20x better than Cassandra in terms of query speed, and more than 10x better in terms of disk compression, right? And even with write speeds, we're like 4.5 times faster. But again, something to note here is that Cassandra was not really optimal for time series at all. We had to add a lot of application functionality and code to make it work like a time series, right? So it was not a good fit at all. That being said, Elastic was closer, but they were really not optimized, right? So you have to really optimize what you write to disk, what you write to memory. You have to optimize the data structure. Search-based data structure is totally different than time-based data structure. Right? So it's under the guts, right? Now, if you don't compare this to any database, but do start looking at a platform, right? Streaming technologies. I'll mention a couple. There's Apache Spark, right? And we saw that one of the reference examples where developers had applied Spark to Influx. So that works, but Spark to me is 800-pound gorilla when I only need a tiny animal, right? So the whole idea here is capacitor layer within Influx is the equivalent of Spark for time series, right? Spark for us, is too complex, too many moving parts. If you have a Spark installation, very fine. You can just use the integration and use it with Influx. But simply too many moving parts, and I still am dependent on multiple databases, be it approximate DB Blink, or having an edge-based database, getting input from an HDFS file system, whatnot, right? And the max throughput. There are, community benchmark rates. Spark could ingest at 400,000 messages a second. Maybe that's a 4 or 5 node cluster, right? We could do twice that at a single node, right? So in terms of infrastructure needed, we are magnitudes better, right? And capacitor has a time series query language. You don't actually need to write or code or decode for time series, right? Because capacitor works on the same data pipeline, shares the same time series data constructs with Influx. So, the amount of code that you need to get it to create analytics is, I would say, nothing compared to the same amount that you would do on Spark, right? If you look at Storm works similar to Spark. It has the bolts and it has essentially your spouts as inputs. But again, that being said, the number of inputs are messages only, right? It's very hard to just get raw metrics in if they are not messages. Throughput was even less than Spark, right? There's a Trident API, there's a Core API. Even with Trident API, 5-node cluster, you're getting 300 messages a second. That's not very high. And the simplicity, right? Do you really need so many moving parts, right? Those are the key differences. But I'll start to, I have a couple more slides. Let me talk about one which is very, very common, which is in the monitoring use case, right? So I spent a number of years working with very large enterprise companies who used to acquire other monitoring tools and build what they call as the manager of managers, right? Where you try to do data correlation. Problem is, MOMs only work well if the underlying data models of each of these silo tools, they share similar format and granularity, right? So you might be collecting data from mobile devices, edge servers, right? JVM, CLRs for your APM applications, maybe synthetics, log parsing, legacy, network packets, whatnot, infrastructure. All of these tools have a different retention period. They have a different granularity. If you're looking at instrumenting a JVM, you might put in an agent and do bytecode instrumentation and look at every execution call going over the wire. But again, you might not want to look at every execution because the overhead might be too high. So in those cases, you might be just looking at a subset of instrumented data. So you could set a frequency at 15 seconds, 30 seconds, a minute, right? That's what we normally see in application level tools. On the network side, however, a lot of network flow analysis tools simply sniff packets on the wire passively, right? They don't actually sit in line. They use span ports and taps. So the overhead isn't there really. And in those cases, you could be doing continuous stream monitoring, but these devices which handle gigabytes of network traffic per second, they have their own processing limits. So a lot of tools persist data in 5-minute resolutions, and there's too much aggregation going on, and there's hardly any correlation, right? So You can try and cobble together multiple tools. Good luck. I worked in companies which did that, and end of the day, too many events from too many places, data not getting correlated, maintaining these integrations can be a real pain, right? Um, Now, the newer generation monitoring tools, they are essentially re-architecting from the ground up, right? Or maybe they are not built by cobbling together too many tools, right? So if there were some legacy or third-party tooling, they would use a transform bridge and get data into data collection queues. And you could be collecting from multiple places, using agents, polling, API polls, synthetics, logs, what you have. Everything is published to a data collection queue. And then metrics and events could be handled separately. And your visualization tiers essentially subscribe to those events or metric stores. And then the data collection queues could be used further to detect anomalies into another queue. And you could have alerts subscribed to that. Now we are getting to a more common data model based approach along this whole layer. Now, if you try to map this to influx, you will see at the bottommost layer, telegraph is where what will fall in place. From the data collection and the metric aggregation is essentially where data influx DB and continuous queries kick in. The anomaly engine is essentially capacitor, anomaly and alerts, and the visualization bit is essentially Grafana chronograph, right? So from a stack perspective, we see a lot of similar architectures. And the fact is, a lot of next generation APM, network, and analytic tools are getting built on top of influx data, right? There's so many examples out there. So I think that's kind of what I wanted to share, both in terms of where this entire segment is heading and why time series is such an important platform. It's almost, I would say, it's the lingua franca going forward for analytics, IoT, and monitoring, right? So if I were you, I would actually try to learn time series, because I think the next 5 to 10 years, the way the market is shifting towards IoT and real-time businesses, and all that data is essentially pure time series data, right? So that's it from my side. Hope this was helpful, and I'll open it up for questions.